Full explanation of carbon film resistors. Fixed resistor. Fixed resistors are a category of resistors in electronics that have a predetermined and unchangeable resistance value, meaning their resistance remains constant and cannot be adjusted or varied. They are the most commonly used type of resistors in electronic circuits and serve the purpose of limiting the flow of electric current in a predictable and controlled manner. Fixed resistors are essential components in various electronic applications and are available in several different materials and configurations. Here are some common types of fixed resistors. Carbon film resistors are a type of fixed resistor commonly used in electronic circuits. They derive their name from the thin film of carbon that is deposited on a ceramic substrate to create the resistive element. These resistors are widely available and are known for their affordability and ease of use. Here are some key characteristics and features of carbon film resistors. The construction of carbon film resistors involves several key components and steps to create a functional resistor with a specific resistance value. Here's an overview of the construction process of carbon film resistors. Substrate. The base of a carbon film resistor is typically made of a ceramic material, such as alumina, Al2O3, or steatite. The ceramic substrate provides mechanical stability and electrical insulation. Carbon film deposition. A thin film of carbon is deposited on the ceramic substrate. The carbon film is created by vaporizing or sputtering carbon material onto the substrate's surface. The thickness and width of this carbon film determine the resistance value of the resistor. Helical or spiral shape. The carbon film is often applied in a helical or spiral pattern. This design maximizes the length of the carbon film on the substrate, which in turn increases the resistance value for a given surface area. The helical shape allows for higher resistance values in a compact package. Tapering. The carbon film may be tapered along its length. This tapering is intentional and helps achieve a relatively uniform resistance value along the entire length of the film. Without tapering, the resistance might vary significantly from one end to the other. End caps. The ends of the ceramic substrate are typically coated with metallic end caps. These end caps serve as connection points for attaching external leads or conductive terminations. They also protect the carbon film from physical damage and contamination. Protective coating. To protect the carbon film from environmental factors, a protective layer is often applied over the film. This protective layer can be made of epoxy or similar materials and helps prevent moisture, dust, and contaminants from affecting the resistor's performance. Markings. Carbon film resistors are often marked with color-coded bands or printed markings to indicate their resistance value, tolerance, and other specifications. The color code is a standard way to visually identify the resistor's characteristics. Packaging. Carbon film resistors are typically encapsulated in cylindrical or rectangular plastic or epoxy packages. These packages provide mechanical protection and make it easier to handle and solder the resistor onto a printed circuit board, PCB. Lead attachments. Depending on the resistor's package design, it may have axial leads, wires extending from the ends, or surface mount pads for soldering directly to the PCB. The leads are typically made of tinned copper or other conductive materials. The primary goal of constructing a carbon film resistor is to create a component with a precise and stable resistance value that can be easily integrated into electronic circuits. The spiral design of the carbon film ensures that the resistance remains relatively consistent across the entire length of the film. While carbon film resistors offer cost-effective solutions for many applications, they may not provide the precision and stability required for high-precision electronics, where other resistor types like metal film or foil resistors may be preferred. The resistance value of a resistor is a fundamental characteristic that determines how much it resists the flow of electric current in an electrical circuit. It is typically measured in ohms, ohm symbol, and quantifies the extent to which a resistor opposes the flow of electrons. Here's a more detailed explanation of resistance value. Definition: resistance is the property of a material or component to impede the flow of electric current. It is a measure of how difficult it is for electrons to pass through the resistor. Unit of measurement:
The standard unit of measurement for resistance is the ohm symbol.
1 ohm is defined as the resistance that allows 1 ampere A of current to flow when a voltage of 1 volt V is applied across it. Mathematically, Ohm's law expresses this relationship as V equals I times R, where V is voltage, I is current, and R is resistance in ohms. Resistance value range. Resistors are available in a wide range of resistance values, spanning from fractions of an ohm, milliohms or microhms, to extremely high values, megohms or gigohms. The choice of resistance value depends on the specific application and the desired electrical characteristics of the circuit. Color code. For many through-hole resistors, the resistance value is indicated using a color code. A set of colored bands or stripes is used to represent the resistance value, tolerance, and sometimes the temperature coefficient of the resistor. Engineers and technicians can decode these color bands to determine the resistor's characteristics. Numeric markings. Surface mount resistors often have numeric markings printed on them to indicate their resistance value. These markings are typically expressed in ohms, kiloohms, k-omega, or megohms, m-omega. Tolerance. Along with the resistance value, resistors are specified with a tolerance, which indicates the allowable deviation from the stated resistance value. Common tolerance values include 1%, 5%, and 10%. For example, a resistor with a 1% tolerance and a specified resistance of 1000 ohms could have an actual resistance between 990 ohms and 1010 ohms. Precision versus standard resistors. Some applications require high precision, so precision resistors with tighter tolerances, example 0.1% or 0.01%, are used. Standard resistors with wider tolerances are suitable for general-purpose applications. Variable resistors. In contrast to fixed resistors with a set resistance value, variable resistors, potentiometers or rheostats, have an adjustable resistance that can be changed manually or electronically to control the flow of current in a circuit. The choice of a specific resistance value for a resistor in a circuit depends on the circuit's requirements, including voltage levels, current limits, and the desired behavior of the circuit. Resistors are used for various purposes, such as voltage division, current limiting, biasing, filtering, and signal conditioning, and the appropriate resistance value is crucial to achieving the desired circuit performance. Tolerance, in the context of resistors and other electronic components, refers to the allowable variation or deviation in the specified resistance value from its nominal or rated value. It is expressed as a percentage and indicates the range within which the actual resistance of the component can fall while still meeting its specified performance characteristics. Tolerance is an important parameter to consider when selecting a resistor for a specific application. Here's a more detailed explanation of resistor tolerance. Definition: tolerance represents the maximum allowable difference between the actual resistance value of a resistor and its specified or labeled resistance value. It tells you how closely the manufactured resistor matches its intended value. Percentage tolerance: tolerance is typically expressed as a percentage of the rated resistance value. Common tolerance values for resistors include 1%, 5%, 10%, and 20%, among others. The lower the tolerance percentage, the more precise the resistor is in maintaining its specified resistance. Example: let's say you have a resistor with a nominal resistance value of 1000 ohms, 1 kiloohm, and a 5% tolerance. This means that the actual resistance of the resistor can vary by up to 5% from the nominal value. Therefore, the actual resistance of the resistor could be between 950 ohms and 1050 ohms and still be within the specified tolerance range. Precision versus standard tolerance. Depending on the application, you may need resistors with different tolerance levels. Precision resistors have tight tolerances, example 0.1% or 0.01%, and are used in applications where high accuracy and minimal variation in resistance are critical. Standard resistors have wider tolerances, example 1% or 5%, and are suitable for general-purpose use. Tolerance and circuit performance. Tolerance plays a significant role in determining the performance of a circuit. In applications where precise resistance values are crucial for proper circuit operation, such as in precision measuring instruments or signal conditioning circuits, resistors with low tolerance values are preferred. Cost versus precision. Typically, resistors with tighter tolerances are more expensive to manufacture, and this cost is reflected in the price of the component. Engineers must balance the required precision with the project's budget. Resistor matching. In some cases, precision resistors with extremely low tolerances are used in pairs or groups to ensure that multiple resistors in a circuit closely match each other.
This matching minimizes variations in circuit performance.
Temperature coefficient. Tolerance should not be confused with the temperature coefficient, which indicates how a resistor's resistance changes with temperature. Both tolerance and temperature coefficient are important factors to consider when selecting resistors for temperature-sensitive applications. In summary, tolerance is a crucial specification when selecting resistors for electronic circuits. It determines how closely the actual resistance of the component will match the intended or nominal resistance. Engineers and designers must carefully choose resistors with tolerances that meet the required precision and performance criteria of their circuits.
Power rating, also known as wattage rating, is a crucial specification for resistors and other electronic components.
It indicates the maximum amount of electrical power that a resistor can safely dissipate in the form of heat without exceeding its temperature limits.
Power rating is typically expressed in watts, W, and is an essential consideration when selecting a resistor for a specific application. Here's a more detailed explanation of power rating for resistors.
Definition: power rating represents the maximum amount of electrical power that a resistor can handle without overheating or undergoing damage. It is the power at which the resistor can operate continuously and safely.
Unit of measurement: power rating is measured in watts, W.
1 watt is equivalent to 1 joule of energy per second. Heat dissipation: when electric current flows through a resistor, it encounters resistance, which causes the resistor to generate heat. This heat must be dissipated to prevent the resistor from overheating and potentially failing. Importance of power rating: selecting a resistor with an appropriate power rating is critical to ensure that it can handle the electrical energy dissipated as heat without exceeding its specified temperature limits. If a resistor is subjected to power levels exceeding its rating, it can result in overheating, drift in resistance value, or even physical damage to the resistor. Derating: in some applications, it's advisable to use a resistor with a power rating higher than the actual power it will dissipate. This practice, known as derating, ensures that the resistor operates comfortably below its maximum power rating, increasing reliability and lifespan. Factors affecting power dissipation: the power dissipated in a resistor is determined by Ohm's law, P equals V squared / R, or P equals I squared * R, where P is power in watts, V is voltage in volts, I is current in amperes, and R is resistance in ohms. A resistor can dissipate more power if subjected to higher voltages or currents, or if its resistance is lower. Examples: a 1/4 watt resistor is designed to safely dissipate up to 0.25 watts of power. A 1 watt resistor can safely handle up to 1 watt of power. A 5 watt resistor is capable of dissipating up to 5 watts of power. High power resistors, such as those used in power electronics, can have power ratings of several tens or even hundreds of watts. Heat sinking: in high power applications, such as power amplifiers or power supplies, where resistors may need to dissipate a significant amount of heat, heat sinking techniques, like attaching the resistor to a heatsink, may be employed to enhance heat dissipation. Temperature coefficient: the temperature coefficient of a resistor also affects its power rating. Some resistors are designed to have stable resistance values over a wide temperature range, while others may exhibit variations in resistance as they heat up. In summary, the power rating of a resistor is a critical specification that ensures the safe and reliable operation of the component in an electrical circuit. Engineers and designers must carefully consider the power rating when selecting resistors to avoid overheating and potential failures. Choosing a resistor with an adequate power rating for the specific application is essential for proper circuit performance and longevity. The temperature coefficient of a resistor is a measure of how its electrical resistance changes with variations in temperature. It quantifies the rate of change of resistance per degree Celsius, degree C, or per degree Fahrenheit, degree F, and is an important characteristic to consider when selecting a resistor for temperature-sensitive applications. The temperature coefficient is typically expressed in parts per million per degree Celsius, ppm/degree C, or parts per million per degree Fahrenheit, ppm/degree F.
Here's a more detailed explanation of the temperature coefficient.
Definition: the temperature coefficient, Tc, of a resistor is a numerical value that indicates how much the resistance of the resistor changes in response to changes in temperature. It measures the sensitivity of the resistor's resistance to temperature variations. Unit of measurement: the temperature coefficient is expressed in ppm/degree C or ppm/degree F, where ppm stands for parts per million. It quantifies the change in resistance per 1 million units of resistance for each degree Celsius or Fahrenheit change in temperature. Positive versus negative Tc. Temperature coefficients can be either positive or negative, depending on whether the resistance increases or decreases with rising temperature. Positive temperature coefficient, PTC, in resistors with a positive Tc, the resistance increases as the temperature rises. This means that the resistance value becomes larger at higher temperatures. PTC resistors are often used in applications where temperature compensation is required, such as in thermistors used for temperature sensing. Negative temperature coefficient, NTC, in resistors with a negative Tc, the resistance decreases as the temperature rises. This means that the resistance value becomes smaller at higher temperatures.
NTC resistors are commonly used in applications like temperature sensors and self-regulating heaters. TC values: the temperature coefficient can vary widely depending on the material and construction of the resistor.
Common TC values for resistors are expressed in ppm/degree C and may range from around 25 ppm/degree C to 5000 ppm/degree C or more.
Stability: for some applications, especially those requiring precise resistance values across a wide range of temperatures, it's important to select resistors with a low and stable temperature coefficient. This ensures that the resistor's resistance remains consistent over varying temperatures.
Compensation networks: in circuits where the resistance of a component needs to be stable over a broad temperature range, compensation networks can be designed using resistors with complementary positive and negative TCs to cancel out the net temperature dependence. Applications: temperature coefficient is a critical parameter in applications like precision instrumentation, temperature sensors, voltage references, and circuits that require stable performance over a wide temperature range.
TCR, temperature coefficient of resistance. TCR is another term used to describe the temperature coefficient of a resistor.
It represents the rate of change of resistance per degree Celsius and is typically specified in ppm/degree C. In summary, the temperature coefficient of a resistor is a key specification that engineers and designers consider when selecting resistors for applications where temperature variations can affect circuit performance. Choosing resistors with the appropriate temperature coefficient ensures that the circuit operates accurately and reliably across a range of operating temperatures. In the context of resistors and electronic components, noise refers to unwanted electrical fluctuations or random variations in voltage or current that can affect the accuracy and precision of electronic circuits. Noise can manifest as both voltage noise and current noise, and it is typically considered as an undesirable characteristic in many electronic applications.
Here's a more detailed explanation of noise in resistors.
Voltage noise, also known as Johnson-Nyquist noise or thermal noise, is caused by the random motion of charge carriers, usually electrons, within the resistor due to thermal energy.
This motion creates tiny voltage fluctuations across the resistor.
Voltage noise is typically described in terms of its root mean square, RMS's value, and is proportional to the square root of the resistor's temperature, in Kelvin, and its resistance value.
Current noise is associated with the random fluctuations in the flow of electrical current through the resistor.
It is directly related to voltage noise through Ohm's law, I equals V/R, where I is current, V is voltage, and R is resistance. Therefore, if the voltage noise is reduced, the current noise will also decrease. White noise, thermal noise, is often referred to as white noise because its power spectral density is constant across a wide frequency range. In other words, it contains random fluctuations at all frequencies. White noise has a flat frequency response and is characterized by its RMS voltage or current amplitude.
Effective temperature, noise in resistors increases with temperature.
As the temperature of a resistor rises, the thermal motion of charge carriers becomes more pronounced, leading to higher levels of noise. To reduce noise, low-temperature coefficient resistors, those with a low-temperature coefficient of resistance, or TCR, are often used.
Low-noise resistors, for applications where noise is a critical concern, such as in precision amplifiers or low-noise audio circuits, specialized low-noise resistors are used.
These resistors are designed to have lower inherent noise levels compared to standard resistors. Resistor materials, the material used in a resistor, can also affect its noise characteristics. Metal film and metal foil resistors tend to have lower noise levels compared to carbon-based resistors like carbon film or carbon composition. Noise spectral density. In addition to RMS noise, engineers may also consider the noise spectral density, which describes how the noise power is distributed across different frequencies.
This is important in applications where specific frequency bands need to be minimized or amplified.
Filtering and signal processing. In some cases, noise can be filtered or mitigated using analog or digital signal processing techniques. Filters, such as low-pass filters, can be used to reduce noise at certain frequencies, and digital algorithms can be employed to process and clean noisy signals. Trade-offs. Reducing noise often involves trade-offs with other resistor characteristics, such as temperature coefficient, cost, and power handling capabilities. Engineers must carefully balance these factors based on the requirements of the specific application.
In summary, noise in resistors is an unwanted electrical phenomenon that arises due to the thermal motion of charge carriers. It can affect the accuracy and performance of electronic circuits, especially in high-precision applications.
Engineers and designers must consider noise characteristics when selecting resistors and employ appropriate techniques to minimize or manage noise when necessary. In the context of resistors and electronic components, stability refers to the ability of a component to maintain its specified electrical characteristics, such as resistance value and other performance parameters, over time and under various operating conditions. Stability is a crucial consideration in electronic circuits, especially in applications where precision and reliability are essential.
Here are some key aspects of stability in resistors.
Resistance stability. The primary parameter of interest when discussing resistor stability is the resistance value. A stable resistor will maintain its resistance value within a specified tolerance over an extended period of time, even when subjected to changes in temperature, humidity, and other environmental factors. Temperature stability. Temperature can significantly impact the resistance of a resistor. Stable resistors are designed to have a low temperature coefficient of resistance, TCR, meaning that their resistance changes only minimally with temperature variations.
Low TCR resistors are preferred in applications where temperature fluctuations are common.
Long-term stability. Resistors should exhibit long-term stability, meaning their resistance values do not drift significantly over the life of the component. This characteristic is especially important in applications where the circuit's performance must remain consistent over many years.
Environmental stability. Resistors can be exposed to various environmental conditions, including temperature extremes, humidity, and vibration.
Stable resistors are designed to withstand these conditions without significant changes in their electrical properties. Moisture sensitivity. Some resistor types, such as carbon composition resistors, can be sensitive to moisture and may experience changes in resistance when exposed to humid environments.
Stable resistors are less susceptible to moisture-induced drift.
Load stability. The stability of a resistor's resistance value should not be significantly affected by variations in the applied voltage or current.
In other words, the resistor's resistance should remain consistent under different operating conditions. Noise stability. In addition to resistance value, stable resistors should have low noise characteristics, meaning they do not introduce significant electrical noise into the circuit. This is crucial in precision measurement and low noise applications. Aging stability. Some resistors may experience changes in their resistance values due to aging effects. Stable resistors are designed to minimize these aging effects and maintain their electrical characteristics over time. Precision resistor types. Precision resistors, such as metal film, metal foil, and thin film resistors, are often chosen for applications that demand high stability. These resistors are manufactured with tight tolerances and low TCR values to ensure stable performance. Calibration and testing. In some applications, resistors are periodically calibrated or tested to ensure their continued stability and accuracy. This is common in industries where precision and reliability are critical, such as aerospace and metrology. In summary, stability in resistors refers to their ability to maintain their electrical characteristics, particularly resistance value, over time and under various operating conditions. Engineers and designers select resistors with stable properties to ensure the long-term reliability and accuracy of electronic circuits in applications ranging from precision instrumentation to critical control systems. Resistors find applications in a wide range of electronic circuits and systems due to their fundamental role in controlling and manipulating electrical currents and voltages. Here are some common and important applications of resistors in electronics. Voltage division. Resistors are often used in voltage divider circuits to create reference voltages or reduce the voltage level of a signal for measurement or interface with other components. Current limiting. In many electronic circuits, resistors are used to limit the flow of current and prevent components from being damaged by excessive current. This is particularly important in LED current limiting, motor control, and overcurrent protection. Signal conditioning. Resistors play a vital role in signal conditioning circuits, such as those used in amplifiers, filters, and sensor interfaces. They help shape, scale, and modify electrical signals to match the requirements of the circuit. Biasing transistors. Resistors are used in transistor biasing circuits to set the operating point, Q point, of transistors in amplifiers and other applications. They determine the transistor's on-off state and amplification characteristics. Temperature sensing. Thermistors, which are temperature-sensitive resistors, are used for temperature sensing and temperature compensation in a wide range of applications, including thermostats and temperature control systems. Oscillators and timing circuits. Resistors are used in conjunction with capacitors to set the time constants in oscillator circuits, such as RC oscillators. They determine the frequency of oscillation in timers and clock generators. Voltage references. Precision resistors are used as part of voltage reference circuits to generate stable and accurate reference voltages for analog to digital converters, ADCs, voltage regulators, and other applications. Load resistors. Power resistors are used as load resistors in various applications, including power supplies and electronic loads. They help dissipate excess power and maintain stable operating conditions. Filtering. In passive filter circuits, resistors are used to set the cutoff frequencies and shape the responsive filters, such as low pass, high pass, band pass, and notch filters. Feedback networks. Resistors are essential components in feedback networks of operational amplifiers, op-amps, and other amplifiers. They help control the gain, bandwidth, and stability of amplifiers. Wheatstone bridges, which consist of multiple resistors, are used for precise resistance measurements and as strain gauges in load cells and pressure sensors. Voltage dividers for sensing. Voltage dividers consisting of resistors are commonly used in sensor applications to convert sensor resistance changes into voltage signals that can be read by microcontrollers or measurement circuits. Pulse shaping. In pulse shaping circuits, resistors can be used to control the rise and fall times of square waves and pulse signals. Power scaling. In audio applications, potentiometers, variable resistors, are used as volume controls to adjust the power level of audio signals. Fading and crossfading. Potentiometers are used for fading, adjusting audio levels between channels, and crossfading, smoothly transitioning between audio sources, in audio mixing and DJ equipment.
Feedback and control loops. In control systems and feedback loops, resistors are used to set gain and control the responsive systems, ensuring stability and desired performance. Pull-up and pull-down resistors. These are used in digital logic circuits to establish default logic levels for input pins and prevent floating inputs. Noise reduction. Resistor networks and damping resistors are employed to reduce noise and interference in electronic circuits. Voltage clamping. Zener diode voltage clamps often use resistors to limit current flow when the voltage exceeds a certain threshold. Current measurement. Precision resistors are used in current measurement circuits, including shunt resistors for current sensing. These are just some of the many applications of resistors in electronic circuits. The specific choice of resistor type, value, and configuration depends on the requirements of the circuit and the desired performance characteristics. Resistors are versatile components that play a fundamental role in shaping the behavior of electronic systems. While carbon film resistors are a popular choice for many basic electronic applications due to their affordability, they may not be the best choice for high-precision circuits where tight tolerances, low noise, and low temperature coefficients are critical. In such cases, metal film, thin film, or foil resistors are often preferred.